Namaste and welcome to the lecture on linear algebra through geometry. Uh, the if you had looked at the previous lectures of this course, uh, we began with system of equations, we began with solving systems of equations, and then we took a complete geometric perspective where we looked at the idea of vectors, and we had looked at interpreting linear combinations of vectors and all those things. We looked at transformations in 2 dimension, transformations in through 3 dimensions, and slowly we started looking at vectors as such, and then we started moving towards the idea of vector spaces, where we define collection of vectors which obey certain properties, and we looked at subspaces, then we looked at the basis and dimension, and then we connected the idea of matrices with that of the idea of let us say vector spaces, vectors and stuff, and we also tried to look at the subspaces associated with a matrix, and we found that given any matrix you have 4 fundamental subspaces associated with this matrix, and we also looked at the idea of rank and the nullity and the orientation of the 4 fundamental subspaces, like 2 of them being subspace of Rn and 2 of them being the subspaces of Rm. We found that the 2 subspaces in Rn associated with the matrix, which are basically the null space and the column space of A transpose, they were orthogonal to each other, and on the other side we also established that the null space of A transpose and the range of A, that is the column space of A, they were orthogonal subspaces. And we said that the column space of A is basically the set of vectors which can be expressed as linear combinations of the columns of the matrix A. And when we say Ax equal to B, our hunt was basically to find out those scalars x1, x2, xn such that the right hand side vector x can be written as a linear combination of the columns of the matrix A. If we said that if B can be written as linear combinations of columns of A, that means you were able to find out these scalars such that this was there, and it is equivalent to saying B is actually in the column space of A. B is in the span of the vectors which correspond to the columns of the matrix A, and everything was fine till now because we could find some scalars, and then we could say that okay, it is there in the column space of A and so on. What if you have, let us again go back to the system of equations, if you are able to find out x1, x2, xn, we say that Ax equal to B, then it is all fine. What if I am not able to find scalars x1 to xn such that Ax is equal to B? How do we interpret that? And when do we do? So when we cannot find scalars x1, x2, xn such that x1 a1 plus x2 a2 plus x3 a3, where a1 a2 an are basically the columns of the matrix A, is equal to B, we say that look, the system of equations were not consistent, right. So what is it to say, I mean when is a system of equations consistent? That is something we are going to look at now. And what is it to say when I cannot find scalars x1, x2, xn such that the right hand side vectors, the right hand side vector B can be expressed as a linear combination of the columns of A? What do we do in that case? When there is inconsistency, what is it that we can do? So that is exactly what we are going to look at in this module. The first thing that we are going to look at is basically the idea of least squares, which we have done before, but we are going to generalize this to across any n-dimensional vector space. We are going to look at the idea of projection in detail, followed by what is called as the pseudo inverse of a matrix, and then we are going to look at pseudo inverse for certain special matrices, and that will be the content of this module. So let us get going. Okay. So where do we start with? The thing is, in the previous modules also we said we had actually had two questions, that we were to answer, where one we said Ax equal to b where we had a solution, and Ax equal to b when we did not have solution. So we are going to address this Ax equal to b when it does not have a solution. Yeah. So let us go ahead. So let us go back to our very first few classes of R2 and let us try to understand from there what is it to say the system does not have system of equations does not have a solution. Let us look at a couple of cases and then let us see, let us try to generalize the idea, right. So that is what we are going to do. So let us start this recall. Whenever, okay, let us consider this, consider the system of equations Ax equal to b consider the system of equations Ax is equal to b. This is what we have. Now depending on the nature of b, we are going to say this. So if Ax equal to b is consistent, if Ax equal to b is consistent, then we had Ax equal to b has either a unique solution or b infinitely many solutions. Whenever we had solution we said that okay the system is consistent. So you have either unique solution or infinitely many solutions. And we said if Ax equal to b is if you had inconsistency, if Ax equal to b was inconsistent or is inconsistent, then no solution exists. That means you can't find the values x1 and x2 xn, so no solution exists. So no solution exists. Right. In which case if you remember we looked for what is called as the least squared solutions, right. So means look for least squared solutions. So the question is, when do we say that a system is consistent and when do we say that a system is not consistent? How do we find out whether a system of equations is consistent or not, right. So let us look at that. So first of all let us try to interpret this Ax equal to b properly. Let us try to understand what Ax equal to b actually means. So let us try to understand that. So look at Ax equal to b. Where A is basically an m by n matrix, real matrix, x is an n component vector and b is an m component vector, right. When we say Ax equal to b, we mean b is equal to x1 into the first column of A plus x2 into the second column of A plus etc plus xn into the nth column of the matrix A. where AI is the ith column of the matrix A. Right, it is the ith column of matrix A. So, what is it that we want when we say solve Ax equal to B, we want to find out. So, when we say solve, so solving Ax is equal to B is basically finding out the value of scalars, finding out the value of scalars x1, x2, xn x1 etc xn such that B can be expressed B can be expressed as a linear combination of columns of A. That means if we can find scalars, if we can find scalars x1, x1, x2, xn, scalars x1, x2, xn, then B is equal to x1 a1 plus etc plus xn an. That means we are going to say the following. We say this implies B is an element of the column space of A. B is an element of the column space of A. If we cannot find scalars, then what happens? If we cannot find scalars, or if there is no scalars x1, x2, xn, find scalars x1, x2, xn, then we say B does not belong to the column space of A, right. That is what it is. B is not in the column space of A. Now, when B is not in the column space of A, naturally I cannot find out the scalar values x1, x2, xn. That means the system of equations correspondingly is an inconsistent system. Now, what do we mean by this? So, the question that we ask is like, how do we know if a given system of equation is consistent or not? Or so the question is, how do we know if a given system of equations is consistent or not? Yeah, if we know that whether it is, I mean if we know that the system is consistent, then we can go ahead finding the solutions. If the system is inconsistent, we know that okay, we have to find the least squared solutions and so on. So, how do we know whether a system is consistent or not? Or suppose I give you a system A and I want to have Ax equal to B, what should be the conditions that B has to satisfy for the system Ax equal to B to have a solution? So, let us look at that. So, let us go back to our very first elementary example that we took. So, let us consider this example 1, where we had this 2x1 plus x2 is equal to 3, 2x1 plus x2 is equal to 4. We already established that this system of equations is inconsistent because you have the same left hand side in both the equations and the right hand sides are different. Therefore, both equations cannot be true at the same time, and therefore the system of equations is inconsistent. That means you cannot find solutions x1, x2. So, what we say, so inconsistency, inconsistent system, and no solution exists. That means for this B that we have, no solution exists. Suppose if I change this B to 3 3, I can find out solution for this. In fact, infinitely many of them are there, right. I can find solution to this if I had taken 3 3 here. Therefore, the question is whether a system of equation is consistent or not, it depends on what is the right hand side that we have, that means what is the B vector that we have. So the question is what condition should B satisfy such that the system Ax equal to B is consistent. In other words, what should be the conditions for B, so that you can write B to be the linear combinations of the columns of A. So how do we interpret that? That is what we are going to see. So let us look at this. Let us not put 3 4 3 3, let us not put anything for the system of equation. Let us just take a simple case where I have 2x1 plus x2 is equal to B1 and 2x1 plus x2 is equal to B2, and the corresponding augmented matrix for this is 2 2 1 1 and B1 B2. This is what I have. Now what do? We take the row reduced echelon form, we do the RREF of this RREF. So the matrix A is basically this 2 1 2 1 and into x1 x2 is equal to, let us take B1 B2. So the RREF is basically R2, if you to get the RREF you do R2 minus R1, R2 tends to R2 minus R1. So what do we get? We get 2 1 B1 0 0 B2 minus B1. So if you see here, if B2 minus B1 is equal to 0, then for such system of for such B values you will have solution. So what do we say? We see that if for solutions to exist, for solutions to exist, for the given example, B1 minus B2 must be equal to 0, right. We will come to this. Now what I do is, I will do a small stuff here. I want to look at what happens to the homogeneous system of equation A transpose y is equal to 0. Look at A transpose y is equal to 0, right. Look at A transpose y is equal to 0 and we will find out something interesting here. So what is A transpose here? A transpose is basically 2 2 1 1 and we have this we wanted to look at the solution to this. So let us take 2 2 1 1 and y1 y2 is equal to 0 0. Now again I will look at the RREF for this reduced row echelon form, where I will say R2 is equal to R2 minus 2 R1. So I get basically 2 2 0 0 into y1 y2 is equal to 0 0. Now we see this, there is a pivot in the first column and there is no pivot in the second column. I mean, therefore y2 is a free variable, therefore I will take y2 is equal to parameter t, which implies y1 is equal to minus t. In other words, the solution to this is y1 y2 is equal to, let me take it as I made a small mistake here, this is b2 minus b1 is equal to 0, b2 minus b1 is equal to 0. So I have t and minus t, that means the set of all values which is t into 1 minus 1 t real, that is the solution that we have. Now let us try to establish a relation between this and this that we have. So if you look at this, B2 minus B1 is equal to 0, I can take this as 1 time B2 minus 1 time B1 is equal to 0, which means I have 1 minus 1 dot product with, okay, B2 B1, let me change that as B1 B2, this I can take it as, this is equal to B1 minus B2 is equal to 0, negative sign out, so I am going to have B1 minus B2 is equal to 0. So I will take this as B1 and B2 dot product. What do we see? We see this B1 minus B2 is equal to 0. That means there is something interesting that is happening. The condition that B has to satisfy is basically B2 minus B1 is equal to 0, is essentially saying the dot product of B with the system, the solution to the homogeneous system of equation A transpose Y is equal to 0, that must be 0. That means the vector B and the null space of A transpose, the vector that is there in your with the solution to A transpose Y is equal, this is exactly what we saw before in the previous lecture, where we said null space of A transpose and the column space of A are orthogonal to each other. So if you want a vector to be there in the column space of A, then the dot product of that vector must be 0 with the vector that is there in the null space of A transpose. So we see that the dot product of this is basically the solution to homogeneous system of equation, or and this is basically the required B. So if this is satisfied, then you will have solution to the homogeneous system of the solution to the system of equation Ax equal to B, that becomes consistent. So the consistency condition is basically saying that, look, you have to basically look at the dot product of B with the solution to the homogeneous system of equation A transpose Y is equal to 0, right. Let us take another example. We just got this one, maybe it could be by fluke. Let us take another example. So let us consider this example 2, where I have 1 1 1 1 0 minus 1 x1 x2 is equal to B1 B2 B3. So we ask, when does this system of equation have a solution? So the question is, for what values of B? Thus the above Ax equal to B has a solution. Right, this is what we are going to look at. So let us do the same thing that we did before. Let us get to the RREF for this. So we have the row reduced echelon form for A. Let us look at that. So what is that? Let us augment this matrix with that B, B1, B2, B3. Now the first thing that I can do is I can take R3, I can take R3 to be R3 minus R2. So I can get this 1 1 and that is B1, 1 0 B2, then I have 0 minus 1 plus 0 is minus 1, so this is going to be B3 minus B2. Now from here let us do the next step. I am going to do R2 is R2 minus R1. So I am going to get the following. So I am going to get 1 1 B1, 0 minus 1 B2 minus B1, 0 minus 1 B3 minus B2. Now I want to make this element 0, so I will write this as R3 is equal to R3 minus R2. So I get 1 1 0 minus 1 0 0 B1 B2 minus B1, and we have B3 minus 2 B2 plus B1, or I have B1 minus 2 B2 plus B3 is equal to 0. This implies B1 minus 2 B2 plus B3 is equal to 0. This is the consistency condition that we have. This is the consistency condition that we have. So let us again do this A transpose Y, let us solve, let us look at, A transpose Y is equal to 0, A transpose Y. What does that mean? I have this 1 1 1 and I have one 0 minus 1 and y1 y2 y3 is equal to 0 0. This is what I have. Now I will do the RREF here, R2 my R2 tends to R2 minus R1. So I have 1 1 1 0 minus 1 minus 1 minus 1 is minus 2. So we have y1 y2 y3 which is equal to 0 0. Now if you see there is a pivot in the first row, there is a first column, there is you have a pivot in the second column, the third row basically the third equation does not have, I mean there is no pivot variable, y3 is not the pivot variable, y3 is the free variable, you have y1 y2 to be the pivot variable, y3 is the free variable. So what do we have? So we have y3 is equal to, parameterize it, make it t, then we have we had this minus y2 minus 2 y3 is equal to 0, which implies y2 is equal to minus 2t and y1 plus y2 plus y3 is equal to 0 we had, therefore we have y1 is equal to minus y2 minus y3 which is basically 2t minus t which is t. Therefore the solution that we have is y1 y2 y3 is equal to t minus 2t and t, which is the same as t times 1 minus 2 1 for t scalar, t real. Now you look at this vector and you look at the consistency condition that we had. The consistency condition that we had was basically b1 minus 2 b2 plus b3 was equal to 0, which means we had b1 b2 b3 dot product with 1 minus 2 1 is equal to 0. Therefore whenever you say that I want Ax equal to b to have a solution, that means I want it to be consistent, this simply means, so consistency condition. Consistency condition. Note that the consistency condition is always on the b vector. So this is nothing but b dot y is equal to 0 for y where y is an element of null space of A transpose. Whenever y is an element of null space of A transpose, the condition is b dot y must be 0. So if b dot y is equal to 0, then Ax equal to b will have solution. We will say will have solution, that means it will be consistent, will have solution. Unique or infinitely many, that we have to see, but you will have solution. The condition is basically b dot y is 0 where y is in the null space of A transpose. Assume that we have a system of equation where in which this consistency condition is violated, that means b dot y is not equal to 0 and you find that you know the condition, the consistency condition is not met, that means the system is inconsistent, in which case what we do is we look for least square solution, and that will be the topic for the next lecture. Thank you.